Assalamu alaikum. Alhamdulillahi Rabbil Alameen wassalatu wassalamu ala ashrafil anbiya wal mursaleen. So this is the sixth lectures on the series of the lectures on the steady state errors. So today's topics is the static error constants and the system types. System types we have studied earlier. Static error constants are associated with the system types, and these static error constants fundamentally determine the steady state error specification. So today we will be discussing in this lecture the static error constant. It is an interesting topic and very important from the design point of view. So watch these videos carefully to understand the meaning of the static error constants and how we can use them in the design problems. The objective is to define the parameters that determine the steady state error specification. So what are those parameters? First thing are the static error constants. So we will be discussing over here three types of the static error constants. The first one is for the step input. So we say that the step input error can be given by E infinity is equal to this we have studied in the previous lecture. So this can determine that when the error will be constant. So the limit s tends to 0 g of s, whenever this is a constant value, we say that there will be a steady state tracking error, and it cannot be made 0. We say to this parameter kp as the proportional constant. So here we say to this one kp, which is the proportional constant. Then we will have for the ramp input, again we write like this, and of course it will be constant error whenever the value is constant. Otherwise whenever this value becomes 0, so 1 over 0, so the error will be infinity. So the situation whenever this is constant or this factor is infinity, we can talk about the tracking errors. So to this one we say velocity constant kp. And then we have the third one is for the parabolic input. The error is like this, E parabolic infinity. So here if you see, there is no s, here is s, and here is s square. And again we say to this ka, here I did mistake, this is kv. So to this one is normally we say proportional constant, velocity constant, and this one is the acceleration constant. If you recall from the previous lectures, I asked you to find out that why to different signal we give the name as constant, and the speed signal and the acceleration signal. So here those are like this one, s g of s is fundamentally derivative of g of s, and s square g of s is the double derivative of the g of s. So here we discuss now for the definitions of the static error constant. We studied on the previous page that position constant is kp. So if this is the position constant, then we say limit s tends to 0 g of s. So this is the position constant, and in this case the steady state step error, like whenever input to the system is a step, then we say it is 1 divided by 1 plus kp. Similarly, For the kv, we will have kv, as we studied before, is equal to limit s tends to 0 s g of s, and in this case the steady state error for the ramp input will be e ramp infinity, which is equal to 1 over kv. So only in the step function you are seeing over here it will be 1, like whenever this is position constant we will get here 1, but in velocity constant and again in the acceleration constant you will not see 1. So here again it is s square, so here is gs, this is position constant. For velocity constant sgs, and for the acceleration constant s square g of s. Why you are not seeing here for the other two s? Because fundamentally when you will write the equation it will become somehow like this. It will be 1 over s plus s g of s limit s tends to 0. So whenever we say limit s tends to 0, so definitely this one will become 0 and the remaining part will be s g of s. And why we are not cancelling here g of s? Because there is a possibility that in g of s may be like s into 1 over s into g1s. So here of course this s can be cancelled with this one. This is why we don't put here 0 with this. Similarly for the third one you will have limit s tends to 0 1 over s square plus s square g of s. So the same reason that we don't cancel, that there is a possibility that this function can have integrators over there, but this one we put 0 directly. This is why we have k is equal to s tends to 0. So here no 1 is appearing, but with them there is no s, and here is also no s square. Here we will discuss an example given to us, like this is the open loop transfer function over here, and for this open loop transfer function we are asked to determine or evaluate the static constants. When we say static constant, fundamentally we are asked to determine the values of kp, position constant, kv, velocity constant, and ka, the acceleration constant. So to them we say static error constant, and then to find the expected error for the standard input for the step input, ramp input, and parabolic input. So the fundamental thing we have to look that determine whether the closed loop is stable or not. So you will find out the closed loop transfer function T of s, and then using the Routh-Hurwitz criterion you will determine that this closed loop is stable. So this work I am leaving to you to do it using the lecture slides given for the stability of the linear system. Now from the steady state point of view, there is one integrator in the denominator. So whenever in the denominator there is one integrator, so what is the type of the system? So the type of the system is type 1. This is number one thing. So without calculation we know that kp is equal to infinity, and the second thing ka will be equal to 0. The only thing what you have to determine, that is ka, and kv we will have to determine. But just for the sake of understanding, as we said that kp will be equal to what? We said kp is equal to limit s tends to 0 g of s. So here it will be limit s tends to 0. So if we write this whole transfer function, so in the denominator we have s and we have these values. So what will happen, because this s tends to 0, so this whole thing will be equal to infinity. And now for the step input, what will be the steady state error? We know that each step, we studied previously, infinity is equal to what? 1 over 1 plus kp, so this will be equal to 0. The second thing, if we look to ka, the acceleration constant, so it is ka will be equal to limit s tends to 0, and this is s square 500 into these things upon s into s plus 8, and this will not make any difference. The only thing, if I look here, is s, and because of s this will become 0. So now if we look to e parabolic infinity, we studied this before, that it will be 1 over k a, and 1 over k, this will be 1 over 0. So this means the steady state error will not be a constant or 0. This means that the parabolic function will not be tracked by this particular closed loop system. Now the only thing which is remaining to find out the kv, and kv is the velocity constant. So finding the velocity constant, it is easy. We know that kv is equal to limit s tends to 0 s, and here of course now we need to insert the values. Upon s into s plus 8 into s plus 10 into s plus 12. So here this s will cancel with this one. If we put here, here and here 0, so we will be getting 500 multiplied by 2 multiplied by 5 multiplied by 6, and here if we put those zeros, here you will get 8 multiplied by 10 multiplied by 12. So this and this is cancelled. This 0 we cancel with this one, so we will have 250 upon 8. So this is the value of kv. And if someone is asking me what will be the ramp, because the ramp error we have to look now, ramp error infinity, this is what? This is equal to 1 over kv. So definitely this will be 8 divided by 250. So this is how we can find out the thing. So the typed version of the system is somehow is like this. So here if you see, as we calculated, so the step error is infinity. This is how you can calculate kp, and this is very definite that whenever you put over here 0, so you will get over here infinity. Then for the kv, if we do the calculation, so this s and this s will cancel with one another. So this s will cancel with this s, and the remaining, if you simplify putting the value, this is fundamentally nothing but 250 upon 8, and then the inverse of that. So this will be your steady state error for the ramp function. So for the step function, the steady state error will be 0. We even don't need to calculate it. We have just to determine the loop is stable. If the loop is stable and this is type 1 system, we know that the steady state error for the system will be 0, because the position constant is infinity. And then for the velocity, we see over here it will be a constant value. And now for the acceleration constant, as we determined previously, it will be s square. So if we look over here, what will happen? This s will cancel with this 2, and normally this is s, so limit s tends to 0, you will get over here 0, and then 1 over 0, so the tracking error is infinity. This means the parabolic function cannot be tracked by using the closed loop of type 1 system. Do you can you think that what should be the type of the system over here so that the tracking error is become 0? Can you answer this question? You see, for the step function, we need one higher integrator. So this means whenever the input was step, to get the 0 error, we need type 1 system. For the ramp function, we need type 2 system. So for the parabolic function, we need type 3 system so that the error should be 0. So system types fundamentally we studied in the previous lecture, so I am not repeating it over here. Here will be just quickly we say that the number of pure integrators in a loop give us the type of the system. Like if there is no integrator, we say no pure integrator, we say it is type 0. If there is one integrator, we say it is type 1. If there are two integrators, we will say it is type 2 and so on. So here you can see the same thing. So it means that G of S has n poles at the origin, because this is an integrator, and when we say n poles at the origin, we means that like this is the S plane, so this is J omega, and over here we have sigma, so the number of poles at the origin are n poles. But of course you have to determine always that the closed loop is stable. If the closed loop is not stable, so whatever we are discussing, it will be not applicable. So the detail of this discussion is given on the next page in the format. So here we say for the step input, the steady state error formula is 1 over 1 plus Kp, and Kp is equal to constant, and it is 1 over 1 plus Kp. This is for type 0 system. For the ramp input, it will be 1 over Kv, and Kv is equal to 0, so the error will be infinity for type 0. Similarly, for the parabolic function, it is 1 over K, K is equal to 0. This is why the steady state error is also infinity. In type 1, the step input, so Kp will be infinity. This means the steady state error for the step input for the type 1 system will be 0. The velocity constant will be 1. Therefore, there will be a constant tracking error in the system, and the acceleration constant is 0. Therefore, the error will be steady state error for the parabolic function will be infinity. For the type 2 system, the position constant is infinity, so the steady state error for the step input is 0, and again the velocity constant is infinity. Therefore, the steady state tracking error for the ramp input is 0, and for the acceleration constant will be constant, so we will get constant error in the steady state error for the parabolic input. So summary of the discussion is over here, like system of type n track an input of order less than or equal to n with ESS 0. Whenever the system n track an input of order n plus 1 with ESS constant, this means that there will remain a constant error in that type of input. And system of type n track the input of order greater than or equal to n plus 2 with a constant with a steady state error of infinity. This means that in this situation no tracking will be accomplished. But for all the cases, for all the cases we have to be sure that the closed loop is stable. So the static error constants like position constant, velocity constant, and acceleration constant, they determines the steady state error performance specification. So let us consider for an example. Someone has given us a control system has the velocity constant is 1000. So what are the information we are getting? The first information is that the closed loop is stable. We know that closed loop is stable. Why? Because this constant will exist only if the closed loop is stable, otherwise it is meaningless. Number 2, the open loop transfer function is type 1. Number 3, if it is type 1 system, for the unit step E step infinity will be equal to 0. Number 4, E ramp infinity will be some constant value, and the reason is that kV is constant, and what is kV is 1000, so this error will be 1 over 1000. This means it will be 0.001. And the fourth thing, the E parabolic infinity will be equal to infinity. This means it will not track this type of system. So the typed version is here of this. The system is stable. The system is type 1. A ramp input was the test signal for this system. The steady state error is 1 over kV and some other. So here is an example we have to discuss. We have given this closed loop, and in this closed loop we have a constant k. We have to find out the value of this, and we are asked that the steady state error is 10%. So one thing we should note that it is type 1 system. If the closed loop stable, so this stability you have to determine by finding the closed loop transfer function and then using the Routh-Hurwitz criterion to show that the closed loop is stable. If the closed loop is stable, then it is very easy because we are saying the error is 10%. So from this we know that the closed loop is stable, otherwise the error will not be a constant value. So first thing, that the system is type 1 system and steady state error will be 10%, can be only for the ramp input, because for the step input the steady state error will be 0 for this particular system because it is type 1 system, and for the parabolic input the steady state error will be infinity. So the only choice is the ramp input, and if it is ramp input we know that k is equal to kv, the velocity constant, which is equal to 1 over E ramp infinity. So this will be equal to 100 upon 10, which will be equal to 10. So kV is equal to 10. Then we know that kV is equal to limit s tends to 0 s into g of s. So this will be equal to limit s tends to 0. I am not going to write this s with it because it will already cancel with this s, and you will be getting over here k into s plus 5 divided by s plus 6 into s plus 7 into s plus 8. So this whole thing, when s tends to 0, you will get 5k upon 6 multiplied by 7 multiplied by 8, and this whole thing is equal to this 10 because this is kV. So I write over here 10. This here you will get 2. So k will be equal to 2 multiplied by 6 multiplied by 7 and multiplied by 8. Then you can use your calculator or something else to find out the number. So you will get a number over here. So the typed version of the solution is somehow is here. So this is the discussion which I did. So read it carefully, and then using the first equation, E ramp infinity is equal to 1 over kV is equal to 0.1, and then kV will be equal to 10, and after that inserting the value over here, this whole thing, like we will take the this 5k upon 336 will be equal to 10, this and this will be 2, so k will be equal to 2 multiplied by 336, and which is equal to this number. Thank you very much. Lecture 6 on the steady state errors completes.